the synthetic methods, there are several approaches. So now, if you really want to understand how easily we can make these methods, I actually tried to make an attempt, and in principle, I have not made this presentation anytime before, but I will do my best. Okay, so whatever way I can. Okay, so if you see the way I organized my presentation is like this. Okay, so I don't take anything from my lab. Okay, so I will try my best not to explain too many things from what I'm doing in the laboratory. Then I will also try to tell you that, okay, so the facilities, whatever you have, I mean, with that, okay, so let it be a BTech laboratory or let it be a MSc laboratory. I mean, with the help of that, okay, so if you really want to do something, okay, so I probably can suggest something at the end of the story. Then actually what I will do, in short, I will try to take you, how will you make a solid in the laboratory? Because most of these things, let it be for catalysis or let it be for sensors or let it be for energy applications, mostly these things are with respect to the solid preparation. So I will try to tell you now, how will you make a solid from a solid? So that means like your starting materials are solids and the final product is also solid. So then I will take you to a very simple method which all of you can use it in the laboratory. Like, okay, so with the, as I said, that always I keep this in my mind, that I'm going to tell you that, okay, you will be using the chemicals of BTech and MSc laboratory. Then I will switch to the solution based methods. Okay, so that means let it be sol gel, let it be precipitation, co-precipitation. There are several ways to understand it. Okay, so I will tell you how the philosophy or the theory behind this one. Then I will take you immediately to, I mean, like the nanoparticles, because you see oxides and sulfides, these are different. And then finally, when you come to, say, for example, nanoparticle, okay, so if you say gold nanoparticle, silver nanoparticle, how can you do it in a reproducible way in the laboratory? So as always, I don't repeat hereafter. I don't want you to use any sophisticated facilities for doing any of these things. I'm sure, like, since after spending for a week, nearly a week, I mean, by this time, I think many of you are aware that, okay, so these particles behave differently. Nanoparticles behave differently because of the change in the redox properties, increasing surface area, or the sometimes even the structural, I mean, the aspects also come in the picture. Especially the morphology is another way to understand, because there is a method which I will tell you, something called polyol method. Sometimes if I ask you to write a representation of a cube or a face center cube, immediately what will you do? All of you will take a cube and try to put some sphere at the corner. But not necessarily that it has to be always a sphere. Okay, there can be a prismatic particle, there can be a triangular particle, so there can be something else. Now, how to make materials with different shapes? This is also one of the things which will be very important, okay, which you will see. Then I finally, like, okay, so you all know that, okay, especially, I mean, these things are known to all of you. Like, especially the nanoparticle is in between a molecule. Molecule is the lowest dimension where you can go, okay? So then the molecule forms as a result of the overlap of the atomic orbitals. So that means the spacing between the HOMO and LUMO is there is ultimate limit one can get. You may say that, no, sir, my teachers told me that, okay, when you decrease the particle size, so the band, the spacing, the energy level increases. How long does it go? If you take a metallic nanoparticle or a metal bulk metal versus actually a nanometal, okay, so the only difference is that's what listed here. The third one shows basically a bulk solid. The first one comes the molecule or simply as a molecule. So in between you have nanoparticles. So these things will show a difference. But most importantly, like, okay, if you come to this one, okay, so if you look at now the way when you decrease the particle size, the clear due to the quantum confinement, the way the spacing is going on, okay, or the way the energy level separation or the isolation is taking place, which actually tells you that this is the ultimate place where you have something called a quantum dot. Okay, so this is something like, okay, you can say quantum well, quantum wide, something. Yeah, but this slide I'm more interested, because every time your teacher tells you that, okay, so take a cube and you try to put a sphere in the corner. But that means we're always assuming that the sphere is the only are the most common way. This is the easiest way to say that whenever you prepare a nanoparticle or whenever you prepare a solid, so unless you have some kind of a special technique followed, unless you have followed a special technique, you normally end up with some kind of a sphere. As long as if the dimensions, if the morphology is the same, that means this is sphere, this is sphere, this is sphere. If you have such a situation, you look at now, this is like 120 nanometers, this is 80 nanometers, this is 40 nanometers. As you can see that there is a clear blue shift. Because once if you decrease the particle size, the spacing you are increasing. Once you are increasing the spacing between the HOMO and LUMO, normally the band gap increases. So you need more energy for excitation. That means that compared to 120 nanometer particle, if you take 80 nanometer particle, you need to supply more energy. This is true as long as you follow one particular morphology. That you can easily see it now. If I take, for example, a 100 nanometer particle, and in principle, you're expected to put it between, okay, so 120 and 80 nanometers. So, but if you see now the way it is shown here, the 100 nanometers, which is extreme left side, so it is instead of a blue shift, now it has gone to a red shift. The reason that here these are all spherical particles, but here there is a prismatic particle. So that means that the morphology also plays a role. Then you may say that, okay, sometime back some teacher told me like, yeah, these things are known to me. Now you tell me, how will you make these materials? How will you make these different shapes? Is there a way to represent, okay, so is there a way, or do I need to follow any specific method to synthesize them in a spherical morphology or synthesize them with some standard morphology? So before I go, as I said that, okay, I will try to classify the whole lecture into based on two parts. One is basically like the oxide preparation. Second one is basically nanoparticle preparation. Metallic nanoparticles are different to the oxides. Okay, so I will first tell you the oxide synthesis. In this case, it is known to all of you that oxides are very stable and thermodynamically stable. That's also the reason why if you take alumina, okay, so which is used while, I mean, in many applications. Let it be as a dielectric material, let it be as a support, okay, wherever. Because oxides are the thermodynamically stable configurations you get. As simple as this. If you take silica, Si, and if you try to heat it in the atmosphere, the ultimate thing, whatever you should get is SiO2. So, but you know that no, the silica is played in several possible ways. Instead of simply taking silica, people go with various ways. Let it be sol gel, let it be hydrothermal, let it be some way, and they try to. In all these cases, they are actually controlling something called kinetics. Otherwise, the thermodynamically stable product is always silica. So that means this is the most stable one you should get. So if you, I can classify them into two categories. One is basically a conventional, another one is non-conventional. When I say a non-conventional method, that means I'm expected to follow some precautions like, okay, some kind of inert conditions or some kind of extreme pressures, okay, these kind of things. But I will tell you mostly the method which you can use it as simple as this. Okay, so that means a powder synthesis using a conventional method. I'm taking one classical example. I'm sure by this time, all of you, I know that all of you are familiar with the basics of solid state. The example, whatever I've given on the slide, if you look at it's actually what you are preparing is MgAl2O4. That means MgAl2O4. This is like AB2O4. That means in solid state terminology, this is basically a spinel configuration. A spinel where it is made up of two materials. One is a magnesium oxide matrix. Another one is basically aluminum oxide matrix. And these two, you are trying to do something finally to get a solid from a solid. So this is mostly called in the literature, this is basically called solid state synthesis, or this is also called the ceramic synthesis, or this is also called the high temperature synthesis. When you say high temperature synthesis, okay, so that means that the meaning is that these two you are mixing it and finally you put it under very high temperature, then you naturally get a solid after some period of time. Then you may ask a question, sir, what is so special about it? Okay, I take these two solids, okay, so then I try to mix them, okay, so then I keep it at say 1000 degrees, I get some product. Now the questions are like this. Who told us to keep it 1000 degrees? And the second thing is when you say you are mixing both of them, you are grinding both of them, how long I need to ground them? Is it like 1 day or is it like 1 hour or is it like 1 year? And what is the effect of it? Then one surprising part is if you look at magnesium oxide and aluminum oxide, I'm sure like all of you know that aluminum oxide has a very high melting point. Magnesium oxide and aluminum oxide, if there is a difference in the melting point, how do I know that what is the minimum temperature that is needed? That means though this technique appears to be very simple, those who work on the structural, chemistry aspects, okay, so if you want to get a highly crystalline material, this is the only method you have. That means MgAl2O4 can be prepared by the solid state, whatever I'm saying now. It can be prepared from a sol gel method, it can be prepared from a precipitation method, it can be prepared from, say, for example, pyrolysis method, argument's sake. If you make all these four materials and try to compare the crystallinity, you will be surprised to see that the solid state gives you the highest crystallinity because you are forcing the structural reorganization. It is the toughest method. It is the very difficult method among all these methods for the following reasons, which I will explain now. That means if you look at now the magnesium oxide, aluminum oxide, ultimately if it has to give you say something like MgL2O4, now you need to worry about what is the crystallographic orientation of magnesium oxide. You need to also understand what is the orientation of aluminum oxide. That means that one of these two has to change its orientation so that you are forming the product. Believe that if the product is taking the shape of or taking the morphology, not the morphology, taking the crystallographic arrangement of aluminum oxide, then magnesium oxide, okay, has to undergo some change. Okay, so whereas the other way, that means then to make it little more complex. Okay, so I can tell you magnesium oxide, if you remember the configuration of the structural arrangement, it is a cubic closed packing arrangement. That means the layers are made up of A, B, C, A, B, C, A, B, C kind of arrangement. That means you have a layer of A, on top of it, you have layer of B. That means you put three fingers on one of the other one in your hand. So that means layer A, layer B, layer C. Then there is a repetition of ABC, ABC, ABC kind of thing. Whereas if you come to the previous one, that aluminum oxide, it has only a hexagonal arrangement. That means your oxide ion is taking up hexagonal arrangement. That means it is only like AB, AB, AB kind of arrangement. That means in one case, you have a network of oxide ions where making of A, B, C, A, B, C, A, B, C kind of arrangement. In another configuration, you have it a material with AB, AB, AB kind of network. So now you are forming a product. That product takes up the shape of only either magnesium oxide or aluminum oxide. Then I will tell you little more details in the next slide, but then you may ask a question, what is the temperature doing here? What is the effect of temperature here? What will happen if there is no temperature? Believe that, okay, you are putting two hands next to each other. When you put two hands next to each other, so if you rub your hands together, that means the boundary of the grain boundary. In other words, you believe that each hand is like a grain. So the grain boundary, that means the surface interface between your magnesium oxide and aluminum oxide is the only reactive zone in all these cases. Then you may ask a question, sir, what do you mean by reactivity here? Reactivity in the sense that the active surface is nothing but the topmost layer of my magnesium oxide and the topmost layer of my aluminum oxide. Then you may ask a question, sir, why this is active? Only the why this layer is active. The reason is very simple. The coordinate to unsaturation is present only in the topmost layer. Bottom layers, the coordination is saturated so that they will not be reactive. That means now the temperature is playing a role in facilitating the migration because the topmost layer, believe that aluminum is in, say, for example, okay, so coordination number of aluminum is argument say 12. So that means that each time aluminum is now coordinatively saturated with 12 neighbors. But the topmost layer, okay, so it is not saturated, so that is the only reactive place. That's the reason why every solid, so it has some, the adsorption capacity. Now the temperature, what it helps is, so since large amount of structural reorganization is needed, the bond breaking of the old ones and bond forming of the new ones, okay, these things require certain amount of energy because once you provide some energy, so then there is something called diffusion. Through the diffusion, one side moves to the other side. It's like you put two hands next to each other. Okay, so like, okay, you put your two hands next to each other. the way I'm putting it and I'm rubbing it like this one. So when the interaction takes place, when the penetration, if it has to take place, so that means that this side ion moves to this side and the counter ion moves this side. So for this to facilitate, the boundary has to play an important role. Since these are thermodynamically stable oxides, unless you supply excess temperature, you cannot facilitate the diffusion. So that means that the rate of diffusion is basically the controlling step in all these cases. That means that if you have temperature, the diffusion is facilitated. So that means that now the question is like, how do I say, for example, sir, I've taken magnesium oxide in one hand, I've taken aluminum oxide in one hand, I'm trying to mix both of them. How can I mix them? You cannot mix them straight away. What you do, you try to minimize the size. Okay, you try to grind them first. Okay, make it as small as possible. So once you try to make it, I'm sure that many teachers would have explained, even I myself said it in the first class, that means you are increasing the surface. If you look at now the first cube, one advantage in this case is this is the only surface. These are 6 faces available for you. Only these 6 faces are the active zones. But the moment I decrease it, now I'm making more and more active sites, so that the first step of this reaction is always like this one. You try to increase the contact as much as possible. Instead of taking simply a bulk solid, now you try to take very, very small, you try to grind it. And you will be surprised that a person grinds for 1 day and a person grinds for 2 days. You will see a difference. The reason is that, okay, you're making smaller. Once you make a very, very small particle, I think by this time, all of you can appreciate, all of you definitely appreciate that, okay, so the surface becomes unsaturated. That means surface becomes reactive. That means the contact point of two hands, okay, so the way I'm showing it here, previously, you see that my solid A and solid B. Now, when I'm trying to put them close, okay, this is the only contact point I have. But now when I decrease the size, instead of this one, say I have it like this now. Okay, so the solid B is like this. When I try to put a contact like this one, now you see the interfacial area is going to be so much. Because the interfacial area is so much, now the reactivity is going to be more. So that now previously the solids are like this one. So each one is a sphere. That means only at one point they can meet. Okay, only one interact. Now the solid I grinded very small, so that now actually I became like this one. I made it like this. So when I increase the surface area, the interfacial area, so now this area becomes more. That means previously you need 1000 degrees. Now you don't need 1000 degrees for doing this reaction. So that means the steps when you decrease the crystallite size, okay, so you know that, okay, so you are increasing now the area of contact. Once you make it, you try to put them as a form of pellet. That means like it's like a grinder, you're putting both of them, then you try to grind them, or mortar and pestle, you try to, say grind it as much as possible. Then you try to pelletize them. You try to pelletize them, that pellet, you can take it and keep it in a furnace of high temperature. Now the question, all of you, the point all of us understand is like you need to make it as small as possible. The crystallite size can be as small as possible. Then you may say a question, one person can say that, no, sir, I used the mixie, whichever is available in my house. The second person can say that I use mortar and pestle. Okay, so I grinded both of them. So what is the difference between that? So when you use a mortar and pestle, the crystallite size can be very small. The third person is using a ball mill, which is available for him. Do I see any difference? Definitely you will see a difference, because the grain size cannot be decreased beyond a point in the mixie you have. In the mortar and pestle, it will be still better, but in the mechanical attrition, whatever you are doing it in the ball mill, it gives you even better or more uniform surface area, more uniform crystallite size. Then you may ask a question, sir, now I understood that I have to make it into the small size. Then to compact it, I need to make it in the form of a pellet. Now I made it as a pellet. Now this pellet, I'm keeping it in the temperature, in the high temperature furnace. Then the one person is asking a question that, sir, I will keep it at 1000 degrees. Then the second person can say that, no, sir, I don't have the furnace because 1000-degree furnace will cost me 45,000. Whereas in my room, I have only a furnace of around 600 degrees. Okay, so, but still I want to do this reaction. Is there a possibility of doing it? Because all these are 1000 is fine, but the moment you go to 1400, the furnace cost will go by 4-5 times. Okay, so then you may say that, no, sir, in the first slide you told me that no, you don't need a hi-fi sophisticated instrument. So you tell me like, how can I do this one? So then the only option you have is you grind it more and more and more. You can do this one. Then the second thing is like you put it in the form of a pellet in a high temperature furnace. then you need to kickstart the reaction. How do I do this one? What do you mean by kicking start of the reaction? You see that you have two solids, solid A and B. One of them has a lower melting point compared to the second one. Then the lower melting point one is the one that actually first gets excited. The surface becomes active, so that the metal ions tries to diffuse to the second direction. And that means if you have two hands putting it this way, so that means like the way I try to tell you, if you put two hands putting it like this one, so the solid A and solid B, if the solid A has the lower melting point, then the metal ions, okay, so they will try to penetrate through the second solid B, then the B ions will also penetrate through the A. If the metal ion is traveling this side, the counter ion is going to travel this side, so that the network is formed like this one. So that means for this to facilitate, you need to provide high energy, you need to provide the temperature. That temperature facilitates two possible ways. One is basically that it increases the rate of diffusion, because you see in the previous slide, I mentioned the Fick's law. Fick's law is nothing but it is governed, the diffusion is governed by the Fick's law. Then the second one is the moment you try to decrease the particle size, you are inadvertently making some defects. Defect is nothing but some kind of crystallographic defects in this case. Okay, so that defect you are bringing up to the surface, so that these defects will act as the nucleation centers, or they will facilitate the nucleation. Then the second point people also off late people do is like, you may say that, sir, I want to prepare now magnesium oxide, or say for example, argument sake MgL2O4. Do you want me to start with magnesium oxide, aluminum oxide, or I take only one? Take magnesium. Magnesium I can take as a metal. Magnesium I can take as a magnesium oxide. Magnesium I can take as a magnesium nitrate. Magnesium I can take as magnesium acetate, whatever chemical you have, like oxalate, acetate, nitrate, okay, sulfate, this kind of things. Now you may ask a question, sir, how do I choose them? Is it going to affect if one student chooses nitrate, another student chooses oxalate, or another student chooses chloride? Will there be any difference? Normally, no, but I think on a microscopic level, if you see the properties very, very closely, there will be a difference, because magnesium nitrate and magnesium sulfate, their decomposition temperatures will be different. So that means both will not give you the same kind of final product. So that means now the way to facilitate the diffusion is basically by increasing the temperature, or if you say that no sir, I don't have 1000-degree furnace, okay, I can never do this one. Even if you say for 2-3 days I can not do this one, then suggest me one method. Okay, then I can say that don't try to start with oxides, then try to start with some kind of sulfates, nitrates, because oxides are more stable, okay, compared to nitrates. Then the nitrate, you can decompose it at 450, 500 degrees centigrade. Instinctively, you're forming, say, magnesium oxide, that you can use it as the starting material. That means though you need magnesium oxide, you need aluminum oxide, you don't start straight away with magnesium oxide and oxides, whereas you can start with the precursors. Then the third part is, sir, I did the reaction, I kept it 600, but even after 100, or say for 100 days, or after 1 year, my XRD doesn't show that I'm forming a new material. That means that, okay, so your nucleation probably did not take place. Then you need to seed something. This is something called a seed method. It's like you are converting milk to curd. What you are doing basically, you are seeding there. Okay, so that kind of a seeding you need to do. That means three fundamental aspects. You try to increase the contact area. Okay, so then try to convert them in the form of a pellet. Then try to ignite the reaction. Okay, so by putting, say, facilitating the diffusion, then try to take it basically try to create the nucleation part. So these are the steps. You try to mix them in the fine powder. Okay, so then the way the starting materials, so just use ball mill, regate mortar and pestle, pelletize it. Then choose the container, because for high temperature reaction, the container should not react. Then try to put the key. Okay, these are the possible steps you have. Then you may ask a question, sir, do I need to always stick to nitrogen atmosphere, or always stick to air atmosphere, or what is the effect of temperature? Instead of oxide, if I want to get a metal, what I have to do? Then you need to reduce it. That means for that you need to have some kind of a hydrogen atmosphere. That means the atmospheres are like oxidizing atmosphere. You have the reducing atmosphere. You can use nitrates. Okay, if you use ammonia or inert nitrogen, you may also sometimes get nitrites. And if you really want to get sulfides, and sometimes people use hydrogen sulfide flow, these are the possible ways. Then how do I estimate this one? You can go with XRD. Okay, this is as simple as this. Now coming to the same, okay, so the magnesium aluminum oxide, whatever I have said for the past 5-6 minutes, now I will convert it in the form for the preparation of MgL2O4. If you take for example, the starting material is magnesium oxide and aluminum oxide. When you try to put them at the interface, what happens is aluminum oxide on the topmost layer. So there is a coordinate to valency there is present with respect to aluminum and oxygen. So that valency will be filled by the magnesium oxide site. So that means aluminum oxide lattice, the contact point of aluminum oxide, you look at one hand as aluminum oxide. So that typically on the surface you have like kind of Al plus 3 and there is some kind of deficiency with respect to oxygen or oxide. Whereas now magnesium oxide side also have the same situation. At the interface now what happens is the smallest of the ions like aluminum plus 3 and Mg plus 2, depending on the size charge, okay, so depending on the temperature, now the metal ion moves from one side to another side and the oxide ion moves from another side to another side. So that, okay, between these two oxide is a bulkier one, so that metal is a small one. So the metal migration normally initiates the reaction. So that, okay, the boundary, whatever you have is like, okay, so initially you have thin layer of magnesium MgL2O4. Now this thin layer, the thickness widens, and gradually this is the initiation. And at one point, then the propagation takes place. At one point, you see the complete network becomes MgL2O4. That means you may say that, sir, it is very easy to, the way it appears very easy. But what are the points I need to look at? Okay, so if you actually look at here, so maybe the next slide it shows, this is the arrangement of aluminum oxide. The aluminum oxide arrangement is with respect to oxide ion, it is hexagonal packing arrangement with aluminum ions filling 2/3 of the octahedral site. Each aluminum plus 3 is in the octahedral network in aluminum oxide. But when you come to magnesium oxide, it is a face-centered cube with magnesium ions occupying in once again the octahedral sites. Okay, so this one. But once if you make the product, this is the product you have. The product takes the shape of the CCP arrangement. Okay, so that means now it takes only the shape of magnesium oxide. Whereas you please understand, in the previous case, aluminum oxide is basically an octahedral arrangement with hexagonal arrangement with hexagonal arrangement. Whereas in this case, this is basically like the CCP arrangement, cubic closed packing arrangement. Now, if you look at your product, the product basically has the final shape of MgL2O4, which is nothing but, okay, so your magnesium oxide network, where Al plus 3 ions are occupying the octahedral sites and Mg plus 2 ions are occupying the tetrahedral site. Okay, so that means that if you look at now the coordination wise, your magnesium is in +4 coordination, the network. Magnesium is in +4 coordination and aluminum is basically the 6 coordination. That means the final network is like the CCP arrangement with respect to oxide ions, where magnesium is occupying the tetrahedral sites and aluminum is basically occupying the octahedral sites. Then you may say one question, sir, I understand I really don't worry about this kind of solid state arrangement. Now you tell me that how do I understand the effect of temperature? The way it is shown here, you keep it at 1300 degrees, you keep it at 1400, you keep it at 1500 degrees. You see the rate of the reaction is going to increase dramatically because the diffusion is going to be more and more facilitated at high temperatures. When you increase the diffusion, the rate, you see simple 100 degrees variation, you see that 1300 to 1400, the slope increased dramatically. So that means the rate increased dramatically. Then go to 1500, then you go to 1600. Then you may ask a question, sir, how do I know that, okay, whether I have to keep it at 1300 or keep it at 1400 or keep it at 1500? Why not 1600? What is the minimum temperature I need to follow the reaction? So then this follows something called a Taman's rule. That rule basically tells that, okay, between the two reactants, that means like if you have two reactants, reactant A has a melting point of 1000 degrees, reactant B has a melting point of, say, argument's sake, 800 degrees centigrade. Then the minimum temperature that is needed for doing the reaction is 2/3 of the lowest melting temperature. That means you have 1000 degrees and you arguments like I choose 1500 and 1000. Because if I have solid A has 1500, solid B has say 1000 degrees, the minimum temperature you need is 666 degrees centigrade. That means if you keep it at 670 or 700, there is a guarantee that the reaction will go. Then you may ask a question, what do you mean by guarantee? When it will complete? Is it like tomorrow, day after, or day after tomorrow? When it will complete? I cannot guarantee anything. I can only say that the reaction will proceed in the forward direction. Then the way logically to explain is, though if I need the 670 degrees, I keep it at 700, the rate of the reaction is slightly better. I keep it at 750 degrees centigrade, the rate is going to be even better. So that means that, okay, minimum 2/3 of the temperature you need for facilitating the reaction. And beyond that, okay, so if you increase the temperature further, then the rate of the reaction is going to increase even further. Then you may ask a question, sir, you choose a very simple example of only two solids. Okay, so it's a binary oxide. You have taken magnesium oxide, you have simply taken aluminum oxide. I want to complicate, I want to understand even for a ternary mixtures or even for a very complex compound. Okay, where I have instead of only two solids, I have A, B, C, three solids, I have four solids. Okay, so can you explain how exactly this goes? Yeah, the way I've written this example, okay, there may be some subscript, superscript differences. Please understand, I modified this slide sometime back. Okay, when Professor Venkateswara called me, I was actually doing something with the slide. So that means now I'm taking you an example of strontium, chromium, tantalum oxide. You don't worry about the formula and all, but you just try to follow the theory what I'm saying it. In this case, I have three solids, starting materials. One is a strontium oxide, I have chromium oxide, I have tantalum oxide. These three oxides I have. Now I want to mix three oxides. Previously, there were only two oxides. Now the first point I need to understand is don't start with the same metals like strontium metal, chromium metal, and tantalum metal. So you need to choose some kind of a precursor, some kind of a starting material. The way I can choose here is the way it is listed here. Strontium metal, it is not easy to handle. Then if I take directly strontium oxide, it picks up carbon dioxide from the atmosphere, and it also has a melting point of 2430. Instead of that one, what I do, I basically take strontium nitrate, so which has a melting point of 570. But main problem with this is hygroscopic. Then I settled with something called strontium carbonate, because strontium carbonate decomposes to strontium oxide at 1370 degrees centigrade. That means when I'm using strontium carbonate, the point I need to remember is what I need is the strontium oxide that has a melting point of basically, say, for example, 1370 degrees centigrade. The same way I can go to tantalum metal. So melting point is very high. But if I take tantalum oxide, so the melting point is 1800. The way I look at chromium, chromium is not very easy in the solid form, in the metallic form. But if I take the chromium nitrate, okay, say chromium oxide, if I take directly, it has a melting point of 2435. Whereas chromium nitrate, nobody can use it because it's a highly hygroscopic material. That means tomorrow, if I want to prepare, say, for example, 5 grams of strontium chromium tantalum oxide, the possible reactions are like this. 4 moles of strontium in carbonate I need to use with 1 mole of tantalum oxide and 1 mole of chromium oxide. If I put these combinations, I get this compound. Okay, say for this compound. That means what you need for this one is the starting material is strontium carbonate, tantalum oxide, and chromium oxide. This many moles you have to take. Not only that means you take these moles, now you look at the melting point of the strontium carbonate, you look at the melting point of tantalum oxide, chromium oxide, the 2/3, the lowest melting point you take, in that take the 2/3 of the temperature. So that slide is not here, but you look at now, believe that this is 2000, this is 1500, this is 1000. Now the minimum temperature needed is basically like, okay, so the 700 degrees centigrade, because that is the 2/3 of the lowest melting temperature. So this is how a solid state method actually proceeds. That means whenever you do a solid state synthesis, so this appears to be very easy on paper. So people say that, okay, so I can simply take solids, I can grind them. Then you need to know how long you have to grind first of all. Then what is the minimum temperature you need to put, you need to know. Then you need to also know that what should be the starting material. The way I've shown here, the strontium can take the pure strontium metal, you can take strontium nitrate, strontium carbonate, strontium sulfate, these kind of combinations you can take. So the one you have to choose should be highly stable, it should decompose easily to give you the strontium oxide. So considering that combination, I've taken strontium carbonate. I don't know how many of you understood in all these cases, the main advantage you get compared to taking the pure metal versus the carbonate, the main advantage you have when you take a carbonate, carbonate decomposes in situ to give you oxide, but also gives you carbon dioxide. So that means any gaseous evolution during the course of the reaction is thermodynamically favorable because entropy of the reaction is increases. Whenever you say that entropy increase, simple, you cannot directly extend it, but taking the extension, the third law of thermodynamic base says that okay, most of the, I mean, the spontaneous reactions, I mean, basically, are the way to understand this one is okay when you take the gaseous evolution, when the entropy change is positive, there is a guarantee that okay you get a good quality material because this is thermodynamically feasible. That means so far I try to say that, okay, solid from solid, the way it appears, it's not that easy. So the way to understand is you pelletize it, take a right precursor, try to grind it, try to pelletize it, put it in a furnace. Now you know that, okay, if you increase the temperature, rate of the reaction increases, then you need to take minimum 2/3 of the temperature for doing it. Then you may say that, sir, it's all fine. Still, I don't have any furnace in my laboratory. Okay, I can only, I have a furnace of simple 400 to 500 degrees centigrade and I cannot go as a, I mean, solid state method because there I have seen that, okay, the temperature is minimum 750 to 800 is needed. I agree. Okay, it's fine. Okay, it's not an easy thing. Okay, but if you have, you can do that because it gives you good crystallinity. Because most of the liquid based, in solution based methods will give you some kind of an amorphous or some kind of a semi crystalline material. But if you really want to have a good crystalline material, so then you need to follow something like solid state. But notwithstanding to the limitation, if you still want to do it, okay, so then you have an option. You can go with the sol gel method. You can go with the hydrothermal or something like the vapor deposition, sonochemical. I will only tell you two methods. One is actually a sol gel based, and then I can tell you very easiest one, the combustion synthesis. Then you can say that sol gel, the way it appears, the name it appears, okay, you are starting with solutions. What happens if a solution pH is changed? If you vary the pH, either to acidic or basic conditions, you normally precipitate it. But I don't allow the precipitation to take place. I start with solutions. I allow them to build the network. That means A plus B, two molecules of the same material are reacting. There is a cross-linking taking place, but still it is not a precipitate. Then if I go on, I allow it, but I ase it, okay, but I don't allow them to precipitate. I don't go to a pH condition where the solubility product is exceeding the ionic product. When do you see a precipitation? Precipitation forms when the solubility product exceeds the ionic product of water. So I don't allow that condition to happen so that I'm always in a gelling stage. Okay, so it's like a semi-gel kind of a stage. That's where I can see. So liquid phase synthesis normally proceeds via several methods. The simplest method people can think of is a colloidal method. Then the second one is a sol gel method. Then you can also use something like microemulsion method. You can also use hydrothermal. And polyol normally is a very specific thing for metal nanoparticles. Okay, so the solution precipitation rules. Okay, so it basically tells that an inorganic metal salt, such as a chloride, nitrate, so on, is dissolved in water. Metal cations exist in the form of a metal hydroxide species. That means say aluminum hydroxide or iron hydroxide. These hydroxides are added with a basic solution such as sodium hydroxide, ammonium hydroxide, something like this one. This is NH4OH. So when you have NH, these kind of bases, so then what happens is basically the hydrolyzed species will condense, will precipitate. Okay, so then finally there will be a network form. Okay, so the way it is shown in this slide. So if you take, for example, some kind of an alkoxide starting material, you dissolve it in water, so then you form some kind of hydroxide. This is basically called the hydrolysis. Then the same material, two of them, they are actually cross-linking basically to give you an extended network like MOM. This is basically one species, this is another molecule. These two are condensing by the elimination of water, and you see that there is a network you are building. Then you see that, okay, the condensation goes on, and it gives you the something called inorganic polymerization. This is how you're forming the network. That means it only tells you that, okay, you need to have a solution, you need to have some kind of a precipitating agent. But some metals, especially like a titanium, zirconium, these starting materials are highly hygroscopic. So you need either inert conditions, or say, if you look at the last equation, it basically tells that during this course of the reaction, alcohol is one of the products that is eliminating out. Whereas to prevent the forward reaction, to slow down the forward reaction, because you don't want to get a precipitate. That's what I'm saying always. Precipitation is the final form of the product. Okay, so you don't want the final form because you cannot do anything after the precipitate formation. So what you need basically is some kind of actually controlled environment. So the third reaction, the way it is shown, alcohol is one of the products. You try to take your starting materials in alcohol solution or some kind of a polymeric solution so that the reaction will slow down. So that means this is some kind of a slowing down of the reaction, so that, okay, so you facilitate this reaction. Compared to these things, the easiest one, whatever I can think of, is basically something called the combustion synthesis. This method is very easy for the reason that, okay, you can actually form oxides very easily in the room temperature. With a simple furnace. Then you may say that, no, sir, in the case of solid state, the reaction took 4 days for me. But in this case, the reaction may take only 10 minutes time, not more than that. So how do I do this one is basically like, okay, so you have a simple theory called the theory of combustion. This is theory of propulsion. Okay, so the combustion of the fuel. You see that you have your metal precursor, you have a reducing agent. So this is like your fuel, like your petrol, diesel. This is like a fuel. You try to burn the fuel, okay, in the presence of a metal nitrate, okay, so that, okay, so you are forming some kind of actually a material, but at the same time, so now you are doing the evolution of the gases like the COX, NOx kind of gases. The way you need to do it is like you see both of them, you try to mix it in this way, the shown in the first picture at the bottom. This is a clear solution. Then you try to heat it. Okay, so when you try to heat it, okay, the water will be eliminated. You form some kind of a syrup. Then you still continue this. Okay, so it's basically foams. Okay, at one point, if you still continue, at one point there is an auto ignition that is taking place. So it's simply done by my colleague. Okay, so on simple heating plate, which is maintained at a temperature of maybe 200 to 50 degrees centigrade. If it doesn't form the self ignition, then in the third stage you can keep it in the oven, which is maintained in a furnace which is maintained at 350 400 degrees centigrade. So then immediately you see the product in 5 minutes. You can form the product. Then here the questions to be asked is, okay, sir, how do I fix this one? How much metal nitrate I have to take? How much, say, sucrose I have to take? Okay, how do I understand the theory? It appears very simple. I can do it tomorrow. But how do I do this one? Sir, can I prepare titanium oxide? Yes, you can prepare it. Can you prepare zinc oxide? You can easily do that. Can I make magnesium oxide? Yes, you can easily do anything which is a combustible thing. Okay, in the presence of a reducing agent, anything can be prepared. Then how do I understand? How many moles of A I have to take it? How many moles of B I have to take it? Okay, that means how many moles of the oxidizing agent, like the nitrate, sulfate, these kind of things. How many moles of the reducing agent? That means glucose. You say that, no, sir, I don't have glucose in my laboratory. I have sucrose. Can I do this? Yes, you can do that. No, sir, I don't have glucose sucrose. I have only glycine. I have only hexamine. I have only citric acid. I have only ascorbic acid. Can I do that? Anything you can do that. Anything you can take it. Then you may ask a question, sir, when we take many of them, what is the rule? What is the principle and the theory behind the formation? The theory is basically called the equivalence ratio. It basically tells that the oxidizing valency by reducing valency, as simple as this. That means I will tell you with an example where O is the oxidizing valency, F is the reducing valency. For example, if you have a compound in that there is a metal present in +2 state, it gets a valency of +2. Metal is in +4, it is +4. Carbon, it is a +4 network. Hydrogen basically gets +1. Whereas wherever there is an oxygen ion, okay, so oxygen present, it gets a valency of -2. And wherever there is a nitrogen, so it gets a valency of 0. Okay, let us go to a calculation. I started mixing two compounds. One is basically TiONO3 twice. This I'm mixing with, say, this is glycine. Now I take only the titanyl nitrate. This is called the titanyl nitrate. This is TiONO3 twice. That means the titanium, I have +4, oxygen, I have -2, nitrogen 0. When I calculate the total oxidizing valency, it gives you -10. The same way I now calculate for the glycine. Now I take the glycine, I try to calculate in the same way based on the formula, it gets the value of 9. That means if you take 10 moles of, if you take 10 moles of the titanium nitrile and the 9 moles of glycine, when I mix both of them, so when I put it at 400 degrees centigrade, this ratio Q by E, the previous slide I've told you equivalence ratio, that ratio is called 1 if you maintain the stoichiometric moles of 10 here and 9 moles here. That means if I take 10 moles of the titanyl nitrate and mix with 9 moles of the reducing agent like glycine, then that ratio becomes 1. In this case, what I see is an oxide form. It's a pure oxide, you will form it. The thermodynamically stable, the total combustion takes place when the ratio is equal to 1 because this is the stoichiometric ratio. What happens if I maintain the ratio of more than 1.1? Okay, more than 2, more than 3. Nothing happens, especially for oxides. But whenever you want to make sulfides, then you may ask, sir, can I also prepare sulfides by using this method? Yes, you can do that. Instead of zinc oxide, if you want to prepare zinc sulfide, the only difference you need is you are taking a zinc precursor, then you mix it with thiourea instead of mixing with urea. If you mix with urea, you get oxide. If you mix with the thiourea, you basically get sulfide. Then you may ask a question, sir, in the textbook I read somewhere that sulfide preparation is not an easy thing because the sulfides are known to undergo corrosion. And whenever you take a sulfide, it also get slightly converted to oxide. So how stable the sulfides, whichever you prepare by this method? They are very stable as long as you maintain the ratio of more than 1.1, 1.2. As I said that if the equivalence ratio of 1, if you maintain, you normally end up with oxides. That means if I take thiourea, instead of taking the ratio as 1, I mix it with 2, I mix it 3 times, 4 times like that. Okay, so then you can make different structures. Okay, so of zinc sulfide. Okay, so that means this method can be used for both oxides and sulfide. How do I make it? This is as simple as this. You take your titanyl nitrate, any oxidant, titanium, any kind of starting, argument sake zinc, okay, zinc nitrate, I can take it here. This I mix with the glycine. I put it in, say, 100 degrees centigrade for some time so that water gets eliminated. That syrup, I straight away put it in a muffle furnace. So then you see that, okay, so there is a TiO2 form. Here the advantage is since I'm using glycine, which is now a combination of carbon and nitrogen, there is a one-step doping of carbon and nitrogen in the case of TiO2. This is probably the simplest method, okay, one can think of. Then you can, these are all only to appreciate that, okay, so we use glycine, okay, I mean, they just only to say that, okay, whenever you use, so, I mean, some kind of combinations we tried, then the particle size can be also controlled, okay, so you can do, this is simple titanium nitrate, titanium dioxide, where the glycine was mixed and it is compared with the commercial TiO2. Now you see that because of the carbon and nitrogen doping, now you see that, okay, so the in situ doping decreases the band gap, then it goes. Then you may say that, sir, what is the principle behind this? You said that glycine, but in my lab, I don't have glycine. And then the third person can say that, sir, in my lab, I have glycine, I have hexamine, I have ascorbic acid, I have citric acid. I want to use 4 of them. Now you tell me that which is the best fuel I have. So the way to understand is you see that the way these are the various fuels I have. Okay, so in that one point of time, so why I'm saying this one in detail is like when I started my work at IIT Hyderabad in 2009, I had only the BTech laboratory with me, nothing else. Okay, so in BTech laboratory, I had found these kind of compounds. Then I told my student, you find out what are all the different fuels you have. Then for months together, she used to collect different fuels. Then fixing the same ratio for the precursor, the metal precursor, we varied now the ratio of the metal precursor. I mean the reducing agent. So like in this case, the glycine, hexamine, tetramine. So now you see that the way I'm showing the stoichiometric equations, this is a fixed one for me. In one case, I used basically glycine. In another case, I used hexamine. In another case, we used the trimethylamine, triethylamine. So like that, I varied it. When I make all the stoichiometric equations, now you see that that gives you the highest number of gases, highest moles of gases. So that normally gives you the better properties. Okay, you see that glycine versus hexamine. Now you see that the crystallite size of glycine is very, very small compared to others. And it has a very high surface area. It has actually lower band gap. In all these cases, it's only TiO2, final product. So that means now you see that it shows you good, and now you see that the percentage carbon doping is also good, and percentage nitrogen doping, and you will be surprised that it gives you, I mean, like I have not shown you the reactivity, so that it gives you good fuel. You will be surprised. Okay, as I said that when I started this work, this girl, okay, she is now somewhere. Okay, she was very worried whether she will get her PhD or not, because every day I was only asking her, get this fuel, that fuel. And you know that at this point, this journal has an impact of around 12 or 12.5, something like. The way, though the combustion synthesis is not my idea, it is known. Professor K.C. Patil of IISc Bangalore, he pioneered this work. Okay, but the only thing I added to this one, or through the lack of facilities in the initial period, is like now we know that, okay, if I give two fuels, I can actually predict it, like which fuel gives you the best one, which fuel gives you better properties for the solid. At the same time, I need to always maintain the equivalence ratio of 1, the way it is shown here. Okay, so the equivalence ratio is always maintained 1 in all these cases. Then you may ask a question, sir, do I need both carbon and nitrogen? So instead of, I can take a fuel which is like ascorbic acid or citric acid, which has basically only carbon source. That means then you can get only carbon doping. In all these cases, it's the same story. You start with an oxidizer like nitrate or whatever. You mix with the fuel by maintaining the ratio of 1. Then you just leave it for a period of time at 100 degrees so that it becomes a thick mass. So that one you try to put it in a muffle furnace at 350, 400 degrees centigrade. In 5 to 10 minutes, it will form the product. The way I'm showing, this is now for the synthesis of sulfides. You see now the beauty, when the ratio is equal to 1, you see that there is an oxide peak also dominant. Okay, so especially when we are not shown up to this, but when you maintain a ratio of until at one point of time 1.1, so until one point of time, you're already seeing the oxide formation. But the moment you increase the ratio beyond 2, that means 1 mole versus 2, equivalence ratio of 2, not mole ratio. It is equivalence ratio. Then you see that start seeing the basically the sulfides and the pure sulfide forms. You can see under at one condition you see pure basic, I mean the sulfide forms. Then this is only for the characterization. The moment you have sulfides, and okay, so then you can actually compare the activity with oxide versus nitride, oxide versus sulfide for some kind of water splitting, whatever. So that means that the solid synthesis you can straight away do with the solid state. Okay, so if your furnace temperature is not sufficient, then you can actually, if you don't have a good furnace which can take you to 1000 degrees, then you can go to combustion synthesis, which anybody can do it in the laboratories. Like, okay, so as simple as this. So that needs a furnace of around 450, 500 degrees centigrade. Then you may say that, no, sir, I want to understand little controlled way how to do this one. This is something called a Sol-Gel method. As the introduction, that slide came at that 10 minutes before I explained. Sol is basically you started with solutions. You're trying to control the precipitation. So by using some kind of a precipitating agent is mostly a base. Now, then the controlled precipitation is something which is giving you a gel. Gel is nothing but water dispersed in a solid. Now you afterwards you are trying to remove the solid, okay, so water, by using some kind of heating called calcination. When you do this one, you basically get something like a gel, I mean something like a final product. That means you have started with solutions, you are preparing a gel. Using the gel, you are trying to build the network. Afterwards you are removing the water to basically give you some kind of a final solid. The way it is shown here, this is for basically aluminum oxide synthesis. Okay, so alumina synthesis. You started with aluminum precursor, like say for example, aluminum, some kind of a precursor. Then I'm mixing with water. So to that, okay, so I'm actually trying to control the hydrolysis. There I'm adding some kind of a precipitating agent, okay, or this actually forms some kind of a precipitate. Then what I do, I try to stabilize it. I get some kind of basically a gelation. Then actually I wait for some time. Okay, so then you see that the way it is calcined at 400 degrees centigrade, it gives you 3 nanometer particle. The way I calcine at 800 degrees centigrade, it gives you 5 nanometer particle. That means the colloidal syntheses are basically the simple methods. These are solution-based methods. Colloidal methods may utilize both organic and inorganic reactants. Typically, a metal salt is reduced to a nanoparticle. Okay, so then the aggregation is prevented. Okay, so by controlling some kind of things which I will tell you. Okay, Then the particle size, so this is basically the powder metallurgy route. Okay, so people say tomorrow, yesterday night, you have seen one advertisement of a Fair and Lovely. Then it has only a zinc oxide inside. Okay, so that zinc oxide in tons and tons prepared by powder metallurgy route. This is actually a powder preparation method. Okay, the way it is done is you have a reactant 1 and you mix with the reactant 2. Then try to understand the temperature effect, to try to understand the stabilizer, try to control the time. This is the aging time. Then you basically see something like your product. That means you are initiating the nucleation. It is forming some kind of a cluster. Then it goes through some kind of a small crystallite. The small crystallites are actually dispersed. Okay, so then finally there will be a growth of the particle, either due to oswald ripening or whichever effect. Then finally you see that, okay, so the aggregates of these particles are basically shown here. The crystallites are shown here. But for this to happen, you need to understand that, okay, when you say that, sir, yesterday in the laboratory, I wanted to do this reaction. I tried to precipitate, I tried to control the gel formation, but somehow I always got a precipitate. Okay, so I could not control the gelling. What could be the reason? The reasons are basically whenever there are two colloidal particles, naturally there is a kind of an attraction between them. There is a kind of a repulsion because colloids are charged. When there is an attraction, when the particle becomes bigger, when there is an attraction, then what you can see is initially flocculation. At one point of time, there is something basically called the aggregation. Whereas when the charge is maintained, the particle is very, very small and the charge is there. The like charges will repel each other so that there is actually a repulsion between them. That means whenever you look at something, the two spherical particles are two particles separated by some kind of a distance, then basically the attraction force between them or the net force between them is as a result of attractive force as well as a force of result of a repulsive force. That means now if you look at the attraction force, this attraction force is basically inversely proportional to the sixth power of the distance between them. So that means that when the separation is too big, okay, so then there will not be kind of any attraction between them. So that means that if the separation becomes smaller, okay, so then the attraction increases between them. That means if you look at now the colloidal particle, there is always a charge on the surface. This charge is basically some kind of a surface charge. Okay, so that means ionization of the acidic and basic groups which are present on the surface will give some charge, especially if you take carboxylic acid. So then you have the N groups are basically CO2 minus. If you take amines, the N groups are like this NH4 plus. It is not NH3 plus, NH4 plus kind of. So that means if the net force is basically an attraction plus repulsion, if the solvent is common, the way to understand the attraction force is by using this formula. The way to understand the repulsion force is by using this formula. But in all these cases, if you don't want particles to come closer, you need to always ensure that the repulsive force is more dominant than the attractive force. Sir, I somehow, whatever I do, like the reaction is precipitating. I could not see it. Tell me what I can do. I can simply tell you that instead of doing in the water medium, you do it in the polymeric medium. Sir, I've done it. Okay, the reaction stabilized now. What can be the reason? The reason is like you are not allowing now the particles because of the viscosity effects, okay, hydrophilic, hydrophobic effects. You are not allowing two particles to come closer. That means that you are decreasing the attraction forces. Because of that, now the net force has basically become still towards the repulsive so that the particle doesn't settle down. Sir, how do I understand this one? You look at now the attractive forces for the repulsive force, the net force as shown in the center of the curve. The net force is the one that is dominant. Now, if you try to play, say for example, this can be understood with something called a double layer theory. Double layer theory basically tells that whenever there is a charged particle, like the way it is shown the plus charge, it will automatically attract the negative charge. So now this layer, the first layer is a very strong layer. That means that there is a huge potential at that layer. But if you try to go away from the first layer, now there is something called an attraction. At the same time, there is called repulsion. This negative charge can get repelled. At the same point of time, there is an attraction force. That means there is a place at one point. There is a place at one point. The strongly held layer and the loosely held layer, they can be differentiated. The potential at that particular point is basically called the zeta potential. That means that you may not understand these things, but your teacher immediately tells you that vary the pH. Once you decrease the pH or increase the pH, when you're doing it, what are you doing? You're trying to create charges. Okay, so you're trying to create either positive or negative charges. When you're creating charges, they will repel each. What happens, like say in your body, there is blood. So, for example, if you say, for example, somebody goes to very low temperatures, you feel headache. Why? Because the viscosity of your blood is going to increase. So now you need to decrease the viscosity of it. What will you do? You take hot liquids or some kind of things. What is it doing? Like basically, it is giving you potential to the body, charging your body. So the way it is basically shown, there is a strong layer called the stern layer. There is a diffuse layer. The potential at that layer is basically called the zeta potential. So for any colloid to be stable, now you need to you need to understand that potential. This is typical to your zeta potential measurement, or like equal to, I mean, very closely related to pH measurement. So that means if I maintain that minimum pH, okay, so then I will be in a position to control the medium. That means the way attraction and repulsion forces you are playing with by varying the pH of the medium. So now your net force can be controlled in such a way that initially you may have something like the flocculation. Okay, so the coagulation, and say for example flocculation, you don't want it to coagulate. Okay, so that means there is no aggregation, nothing. So always you need to ensure that, so you maintain minimum pH. That pH, that means now the way to understand, the way to stabilize colloidal particle. Sir, yesterday I prepared a silver nanoparticle, but today it is not stable. What I can do? Actually, I can tell you a method how to do this. There are only two options for you. Instead of doing it in water medium, you do it in a polymeric medium, little bit of a polyethylene glycol or some kind of a polymer you add, then the reaction slows down. Otherwise, you can put something called a capping agent. So when you put a capping agent, you can also control the precipitation. Okay, so that means you don't allow the particles to come close because the charges are not attracted to each other now. You're preventing the attraction between them. So that's why you can do. This basically boils down to something called the electrostatic stabilization. There is something called a steric stabilization. So that because of these two, the colloidal particles actually become stable. That means that you start the events because of the collision, there can be aggregation, there can be stable. Aggregation can be prevented by using actually a coagulant, or kind of some kind of an electrolytes you are using, or some kind of a polymers you are using. Because of this, you don't allow them, okay, so to precipitate, okay, so that there can be a flocculation or some kind of a coagulation. Basically, this came once again, okay, so this I already told you. This I already told you. Okay. Yeah, then you may say that, sir, now I understand that, okay, now you told me initially oxides, then you actually went to, say, for example, initially you followed the solid state, then you went to oxide preparation. But, sir, now I also want to prepare a metal nanoparticle preparation. Okay, so the oxide is one part, sir, but titanium dioxide as such is not active. So I want to put gold on that one. How will you make a gold nanoparticle? If you take literature, it's very simple. Nanoparticle synthesis is very, very easy. Like I just took it from the literature. It is not mine. You simply take your silver nitrate, argument sake. Okay, try to take a beaker. Okay, so on that put hot water, water and heat it. Okay, and you take now silver nitrate, add some amount of silver nitrate. To that one, you can add, say, a little bit of a sodium citrate. Okay, so you see that you start heating it. So you just wait for a minute. Okay, so then you see the color formation. That actually tells that, okay, silver is reduced to silver zero. Then you say that you leave it for some period of time, it forms. Then you may say that, sir, now I do at 40 degrees centigrade, I do at 60 degrees centigrade. Do I see a difference in the particle size? Yes, you should see a difference. How do I know that? Is the color is in the little pale yellow, but the moment the particle size is little bigger, then you start seeing the color of reddish kind of brown or brownish colors. So that means by UV visible, just by looking at for silver, now you can say that this is a 10 nanometer particle and this is basically a 40 nanometer particle, argument's sake. Then you may say that, no, sir, I don't want to do it in a random way because I don't know how to control it to a 40 nanometer or how to control it to a 20 nanometer. Now you tell me a controlled method, how do I do this one? Okay, so this is also once again you follow a colloidal method. Basically, in all these cases, you are using some kind of actually a reducing agent, say something like sodium citrate or I mean like the sodium borohydrate, these kind of things. Normally, these things are good if you want to get a particle size of around 30 to 40 nanometers. So if you especially citrate is proven to be a good capping agent for gold. The way the reaction goes are basically you are the gold, so you need to reduce it to form AU0. When you have citrate kind of a capping agent, okay, so especially you actually form this kind of things. Okay, these electrons will be now donated. Okay, so they are like the cappings on your material. You just try to take the one way you can do this one is basically you try to take the chloric acid, auric acid. Then you try to basically say, for example, you add a reducing agent, you leave it over a period of time. Then by looking at the color, actually you can say that whether the particle is reduced or this gold is reduced or not. It is as simple as this. So the way it actually forms is initially you have the nucleation. You start heating them, you start aging them. At one point of time, you form some kind of a cluster. At one point of time, it basically forms some kind of a seed crystal. The way you control the growth of the medium, that means all the spherical particles, the growth is always in three directions. Then you always get in the spherical particle. But whenever the growth is taking place, okay, so the all the sites, okay, are not growing in the same fashion. You are adding some kind of poisons, okay, some kind of substance which will irreversibly adsorbed on some planes, so that the growth will not go in that direction. So that means that's how you basically get some kind of a cylindrical particle, so compared to a spherical particle. So this is basically very simple to understand with respect to your some famous method called polyol method. That means the reduction of silver nitrate by sodium borohydrate can actually give you a very, very small particle. If one reported method, the reduction takes place in the presence of layers of actually some kind of a clay, then you start seeing that the clay particles will control the shape of your silver nitrate. Okay, so that now instead of forming a simple spherical nanoparticle, it actually forms some kind of a prismatic particle. The way to understand this one is this boils down to something called the microemulsion method. That means that you don't do the reactions purely in water medium. Though, because I want to tell you a controllable particle size. That means today you prepare 10 nanometers. Tomorrow exactly you want to produce 10 nanometer particle, only 10 nanometer particle. How do I do this one? This is basically called microemulsion method. The way to understand is depending on, the surfactants. All of you might have heard surfactants like AOT surfactant, acetyl trimethyl ammonium bromide. So these kind of things have, when you dissolve it in water or some solvent, depending on the solvent you are using, there is a hydrophilic place, there is a hydrophobic place. So when you try to dissolve them, all hydrophilic places will come at one point. All hydrophobic moieties will be arranged at one point, so that there is a clear difference between a hydrophilic and hydrophobic place. This is basically called a micelle. When you actually have a micelle, depending on the polarity of the medium, if say, for example, if this is in water medium, this is a hydrophilic and the tail is a hydrophobic. When you put any polar compound, that goes into the hydrophilic medium. So if you put any hydrophobic one, that basically settles somewhere on the surface. So depending on the way which surfactant, whatever you're using, the way you are controlling the radius of the micelle can be controlled by taking water to surfactant ratio. That means this water and this surfactant, this mole ratio, when you control them, so then you can control the micelle core. So when you control it, when you add any hydrophilic in, when you add water, it only goes here, it doesn't go anywhere. So that means that hydrophilic interactions are something which are going to form. Actually, I'm showing you one example with respect to palladium. Okay, now you take, for example, I have taken isooctane and water. Okay, so as the medium for me. When I take isooctane and I take a surfactant, this is dissolved in water. When I dissolve it, okay, so there is a linear curve which is missing. You believe that it is going through origin, which is not shown here. Depending on the way I control water to surfactant ratio, then I can actually control the particle size the way shown here. So that means now if I need to take 4 ml of water, I take 2 ml of water in isooctane, another 2 ml of water in another isooctane in another test tube. In one of them, I take palladium precursor. In another one, I take sodium borohydrate or hydroxylamine, something. Then I mix both of them. When you add both of them together in the same beaker, then you see that there is a hydrophilic exchange should take place. Because of this, yeah, the way it is shown here, you are taking a reducing agent in one case and you are taking actually metal in another case. You try to mix both of them. Okay, so when you mix both of them, both are taken it in water. So now you see that the initial part, okay, there is an exchange with respect to hydrophilic. So then you see that this metal nanoparticle size is basically controlled by the micelle core, whatever you have. When you have a metal ion, you are adding a reducing agent. So then initially it forms some kind of a nucleus. Then when this is a reversible reaction, when you control it, you are now essentially what I'm saying is the particle size is actually controlled by the size of the micelle you have formed, hydrophilic core, because I've taken both in water, metal in water, reducing agent in water. When I mix both of them, water should mix with water, so that okay, so now you see that the metal particle is going to stabilize it. This AOT especially is like this one. When you try to dissolve it in isooctane, okay, so this is how it is going to be. To this, I'm adding now the metal precursor. Okay, so this is taken from the literature. When you try to do this one, this is the clear solution in the beginning. When the reaction takes place, the way it is shown, okay, this is how the solution turns color. So that means I leave it for some time, then I use, say, rotavapor basically, and I redissolve it in, say, for example, some solvent. So then I see that these are the metal nanoparticles, whatever you have. The tongs, the strong, the liquor, whatever you have, okay, so that is what it basically gives to the metal nanoparticle. So that means one way of preparing the reproducible way is also like this one. You use something like the reverse microemulsion. Okay, so this is like an emulsion because oil dispersed in water, but in this case, water is less, oil is more. That's why this is like the reverse microemulsion. Okay, so you have added these things. Okay, so in one of the things you have taken metal precursor, in another thing you have taken, say, for example, your reducing agent. Just you mix it. Okay, so the reaction you can see it in front. The need of the micelle is basically to control the particle size. This is one of the highly reproducible methods. You can also follow several methods, okay, by using the solution. Simply like without any capping agent also you can do that. You take a nickel nitrate solution, just put with a reducing agent. Okay, so then you see that the metal forms, but you see that here the particles are not uniform. Okay, so that's why you need to have a capping agent. This is known, especially like the way the temperature plays, the way concentration, pH and composition, these things are basically going to control. But for all these things, you need to have some kind of a seed to start with. So then you need to add some kind of complexing agent. Okay, so if for example, pure silver, you take it like to silver zero reduction takes place at say this much voltage. But the moment instead of pure silver, you take it like a silver complex of say for example, okay, so silver nitrate, okay, so silver ammonia complex. So then basically that gives you the silver zero basically takes place at a different potential, or the KSP value is different. So especially cyanides, you take it for example. That's the reason why mostly gold and the silver are worked with cyanides. Okay, so what I'm trying to tell is the way you start with the precursor, it is going to affect. Okay, so the KSP value is going to be different. So the equilibrium constant value is going to be different, and the precipitation constant is different, and the potential at which the precipitation takes place is also different. Okay, so this is one part. Then you, what people do is like, take silver or gold salt and try to put with sodium borohydrate. Initially, you form a spherical particle. That spherical particle, you try to take it and try to take it in a metal salt or some kind of a capping agent, so that this will be a capping. Say, for example, all the three directions is isotropic medium. When you add this one, this preferentially adsorbed on one side, so that the growth cannot take place on that side. So then you don't form a sphere, you form what you basically call is like a cylinder or some kind of a prism, some kind of hexagon, these kind of things. For that to happen, you need to follow something called a polyol method. That basically mostly goes with some kind of a capping agent. So most of the places people use citrate as a capping agent for gold, or even CTAB is a capping agent. If you use citrate as a capping agent, okay, you form one kind of things. If you use basically CTAB as a capping agent, you form rod-like morphology. That means the morphology also goes in a different way. Then comes with, for example, so the reducing agent concentration, you are also varying it. You see that the way you are taking it in AOT solvent, your starting material is the same, your surfactant is the same, but the way your starting concentration of the gold is the same. The only difference in all these cases is you have added citric acid concentration. You are varying it, the trisodium citrate, you have added. When you vary it, now you see that depending on the way you're varying the percentage, now you see that the color is going to be different, and you see that lambda max is going to be different. Then you see that the particle size is also going to be different. These are the known methods. Okay, so in the literature, I'm not actually trying to show anything new. Then the way you start with micelle, then the way you try to arrest the propagation in some directions. You can also see that, okay, the kind of a particle initially takes up the shape of a different shape, then it forms some kind of a cone, some kind of joints like this. Okay, so these are the initial methods which are actually reported by various groups. So the way actually I try to tell you is like, that's all I wanted to tell you. I stop at this point. I wanted to tell you that if at all you want to go with the simplest method, okay, so what you can go is something like the solid state method. But the solid state method, the main problem is that, okay, so you need to always need a high temperature furnace. But even solid state method, though it appears to be very simple, the way to control the chemistry is like, okay, you need to make it as small as possible. Try to make it as a pellet. Then you need to understand what is the temperature. You need to understand, are you operating minimum 2/3 of the temperature or not? Then solid, sir, I don't have the furnace. Okay, 1000 degree. Tell me a method which can go with the 400, 450. The easiest one basically is the combustion synthesis. For this, you don't need to have a specific fuel as reported in any paper. You can use any fuel, but you need to understand how many moles of the fuel has to be taken to replace the fuel reported in the literature. Then you need only a furnace. Sometimes you don't need any furnace. You keep on heating it in a, the heating plate. There can be a combustion in front of you. But to initiate the reaction in 5 minutes, you can put it in a muffle furnace of 400, 450. No, sir, I want to do with the solution methods. Okay, so then there is something called a simple precipitation. But precipitation always gives you amorphous. Instead, you can start with the sol-gel method. So the solution you are trying to control. Okay, so the stability of a gel is explained with respect to colloidal solution, where the like charges will try to attract. Okay, when the particle becomes bigger, it will agglomerate. To prevent this one, you need to maintain the opposite charges. That means like charges will repel. Or another way of doing it is you put a capping agent so that they don't come to each other. This is another way of doing it. Then to prepare metal nanoparticle, any reducing agent you need, but to get it in a controlled way, you can actually follow reverse microemulsion, which is a very sturdy and a very robust method for doing it. Okay, so that's it. After my last presentation, there were 2 students called me and asked me for this one. And thanks a lot to Professor Venkateswara Rao for accommodating me. And as usual, I will be very happy to take up any questions that you may have. Okay, thank you.
Sir, thank you very much, sir. It was like a 1 semester course, I felt actually. The total synthesis you completed almost all. Thank you. Thank you very much. Except core shell kind of things. Other than that, you almost completed things.
Sure,
Thank you, sir. Thank you very much, sir. So I request Shainita, if any questions are there in the chat box, please.
Sir, our first question is how we can get monodispersed particles.
Yes, sir. Yeah, a monodispersed particle, especially spherical, is a very common thing. But when you have several shapes, normally it is not an easy thing. But unless you control the medium, say for example, why a different shape forms compared to the first shape? The reason is that when the growth of the particle is taking place, either the particles got fused, that means they agglomerated, then the particle size becomes bigger. This then another possibility is like when the growth of the particle is taking place, it doesn't grow uniformly in all the 3 directions. When it doesn't form uniformly, that means that believe that there is a sphere. In the sphere, from the center, if you want to look at the outer surface, this is equal, no? Like anywhere on the sphere. But now that means that all the planes, like all planes are equally exposed to the reaction medium. But whenever now you in your reaction, there are some the capping agents, or there are some metal ions which are known to adsorb in a particular plane, then the growth will not grow in the direction. For the growth to happen, the 2 particles should come closer. When there is an irreversible adsorption on one of the planes, in that particular plane, the growth will not. It's like this one. So a person standing in the 4-road junction, he can go in all the directions. But if you close one of the ways, okay, then he cannot grow in that. He cannot go in that direction. That means that he is forced to follow a different path. That means instead of a spherical, now you normally end up with a different shape particle. Now the way you are controlling, okay, so the way you are adding, say for example, sometimes a sulfide is kind of a capping agent. Sometimes CTAB is a capping agent. So like this, these capping agents, whenever you do, they preferentially adsorb, but they get stayed with one of the planes, okay, so that the growth will not take place in that direction. That means, to answer you in a simple way, you need to selectively poison one of the growing directions so that now the growth will not take place in that direction. So that's it.
What are the requirements for the control of size, particularly in polyol synthesis?
Yeah, the growth, see, basically there are four effects. One is basically concentration, the second one is temperature, the third one is the time, the fourth one is basically the capping. These are the four methods wherever you have it. Normally you do something called a seeding method. Say, for example, a seed method, you have added and you waited for some time. That means you allowed the reaction to grow until one point of time. Then if the time is, if all others are constant, then you end up with one shape. Then if the same condition you vary the time, then normally you may get a different shape or a bigger particle. The reason that the aging and the redeposition, see, for example, when you take actually what you call, okay, hydrothermal synthesis, one way to explain the particle growth is also basically like equivalent to Oswald ripening. That means the small particles will be digested by a bigger particle so that the particle grows. One way to control it is basically is like, okay, you have the same temperature throughout, same concentration throughout. So that means that then the time is the only thing which is varied. Okay, so now the variables are understood, then you can get a reproducible particle. So the of the four combinations you have, concentration, time, temperature, stabilizing agent. So if you are trying to carefully play with all these things, then normally you get the same shape. Okay.
Which method is better for preparation of hydroxide composites?
Normally, see, hydroxides are mostly amorphous materials, unless the clay materials like double hydroxides. The hydroxide is not kind of the thing you need. You need hydroxide, two hydroxides come closer, there is a condensation. The condensation basically gives you a metal oxide. If your objective is to get a metal hydroxide, so then any precipitating agent will normally do it. Okay, but if your objective is to get a precipitate and recalcine it, to get an oxide, for that to happen, okay, you need to facilitate the condensation. Okay, so hydroxides as such, okay, so I don't see anything, but depending on the pH, okay, you can control the precipitation. But if your objective is to get an oxide from hydroxide, you started with metal nitrate, you convert it to metal hydroxide. These metal hydroxides are individual moieties in the solution. But when you want to bring them close, okay, and then you can add a precipitating agent like sodium hydroxide, ammonium hydroxide. So then what you see is like you convert them to some kind of, initially metal is in the hydration sphere. Then you convert them to metal hydroxides. So that precipitate, whatever you get is nothing but your metal hydroxide.
Sir, please suggest some simulation software tools for nanomaterial synthesis.
Sir, to be frank, I don't know, sir. I never did anything. I use computer only for presenting and typing, and I don't know anything about simulation. But I am not really sure. But there is a way to do it, okay? But I really don't know. I cannot comment on this.
Thank you, sir. We are done with the questions.
Okay, fine. Thank you very much.
Thank you very much, sir. It was once again, I thank you. The interest you took and the presentation was fantastic, sir. Thank you, sir. Thank you very much.
Thank you. Thank you. Okay.
So for today, we are going to leave the session. And tomorrow by 9:45, please join for the last day. Thank you. If any questions are there, please post in the Telegram or WhatsApp groups. Thank you. Shiva Garu, we can leave.
Okay, sir.